Okay, so now we come to the Riemann problem, which is really the fundamental sort of problem that's a building block for the numerical methods we'll be looking at, as well as being key to understanding a lot of the theoretical analysis of hyperbolic problems. And we'll start with just linear systems of equations. Actually, we'll start with the linear advection equation, scalar equation, and of course just in one space dimension for now. So the Riemann problem for a hyperbolic first-order PDE consists of whatever hyperbolic equation it is that we're studying, together with special initial data that's simply piecewise constant with a single jump discontinuity at x equals 0 typically, although when we look at finite value methods, we'll think of the jump discontinuities as being at the interface between each pair of grid cells. But in terms of the general theory, we typically think of it as being at x equals 0. So we start with initial data that has just a single jump discontinuity, and then it turns out that you can often write down the solution of this Riemann problem. Certainly for linear systems, we'll see that it's relatively easy, but even for nonlinear systems of equations, where the solution could be quite complicated in general, the Riemann problem often has a relatively simple structure. It's a similarity solution where the solution depends only on x over t and expands out as a set of waves propagating away from x equals 0. But if we look at the simplest possible case, the scalar advection equation, linear constant coefficient scalar advection equation, then if we have discontinuous initial data, q of x0 is just this jump discontinuity, then as with any initial data we have for the advection equation, constant coefficient problem, the solution simply shifts at constant speed u. So the solution at time t is q of x minus ut. And so you still have the same jump discontinuity, but it's propagating at speed u. And in terms of the numerical methods that we'll be looking at later in particular, it's often very useful to think of this as a wave, a single wave that's coming out of this Riemann problem, and I'll use these script w's for the waves. And in the case of the scalar advection equation, there's only a single wave, which has a jump across it that's equal to the jump qr minus ql, and it propagates with speed s1 equals u. We'll see for a more general linear system that we get a set of waves that are proportional to eigenvectors, where we have to split up qr minus ql into eigenvectors, and the speeds they propagate at will be the eigenvalues. But in the simplest case of advection, if we start with initial data down here at the bottom, that's just a simple jump discontinuity starting at x equals 0. Then as time evolves, in the xt plane, we'll have this sort of structure where there's the single discontinuity is simply propagating with speed u, and everywhere to the left of that in the xt plane, the solution is equal to ql. Everywhere to the right of that, it's equal to qr. And at the top is just a representation of what the solution q looks like at this later time. So ql and qr would be the left and right state, and this jump would have moved from x equals 0 up to x equals u times capital T at time t would be the location of the discontinuity at that time. So one important thing to note about the Riemann solution is that it's not a classical solution of the PDE, because we can't differentiate the discontinuity and just plug it into the differential equation and see that it's satisfied. In fact, for the Riemann problem, when we look at qt plus uqx equals 0, q is just identically constant except at this discontinuities. So almost everywhere this PDE is just saying 0 plus 0 equals 0, which isn't very interesting because the x and t derivatives are identically 0. But at the discontinuity, the time derivative and the x derivative both blow up. And so you can't really see what the right structure of the solution, the right propagation speed is necessarily from the PDE. For the advection equation, we can easily show that for any initial data, the solution is simply shifting at speed u, and so for the discontinuous initial data, that's the right thing too. But when we start talking about shock waves and nonlinear problems, it will be sometimes difficult to read that off from the PDE. And so then it's useful to go back to this integral form of the conservation law, where we're looking at the integral of Q over some interval and how that changes with time based on the fluxes at the left and right edge of the interval. And we could even integrate this in time from t1 to t2, in which case we find that integrating the time derivative from t1 to t2 gives us the difference in this integral at time t2 minus the integral at time t1 from differentiating this term, and from integrating that term from t1 to t2. And on the right-hand side, if we integrate the fluxes from t1 to t2, we get this integral and this integral at the edges. So we can write the integral form of the conservation law. We can actually sort of integrate it to see that the integral over a given section from x1 to x2 changes from time t1 to t2 based on the integral of the fluxes at the two edges of the interval x1 to x2. And this sort of integral formulation makes sense even if they're discontinuities. The integrals are well defined even if there's a jump discontinuity of these quantities somewhere in between x1 or x2, or somewhere between t1 and t2 along x1 or x2. And so this makes good sense even for discontinuous solutions. And also when we look at finite volume methods, this is exactly the sort of formulation that we'll use, because we'll think of x1 and x2 as representing the endpoints of some finite volume cell, and we'll go from some initial time up to some later time t2, and we'll be looking at how the integral of Q changes from one time to the next based on the integral of the fluxes in time along the two edges of that interval. You can also sort of interpret this discontinuous solution as being the limit as epsilon goes to 0 of the solution of this parabolic equation, the viscous equation or dissipative equation, where we put epsilon qxx on the right-hand side. This was discussed before. So this equation, as long as epsilon is positive, has a smooth solution for all time. Even if you start with discontinuous initial data, it smooths out immediately. But as you let epsilon go to 0, the sharpness increases, and so you can look at the discontinuous solution as being the limit of this viscous solution, vanishing viscosity limit, which will also be a very useful way to look at things when we talk about shock waves. Okay, so the solution of the Riemann problem for the Advection equation is so simple. I don't want to spend too much more time on it, but I want to take a brief detour here to talk about this book on Riemann problems and Jupyter solutions that we came out with a couple of years ago, that illustrates the solutions to Riemann problems for a lot of particular applications. And I'll just show you the Advection notebook to start with, but I encourage you to look through other notebooks. We'll also look at acoustics later in this lecture. So if you click on this top green web page here, it takes you to this page, which lists several ways that you can view these notebooks. So you can download or clone a Git repository that has everything in it that you need to actually run the notebooks on your laptop, but with some instructions of various other software that you need to install to make them work properly. But if that's too intimidating, then there's a couple of easier ways to get going with these notebooks. One thing you can do is just view the notebooks as HTML files that have been rendered by running the notebooks and saving the HTML. And you can see a lot from that view, although some of the interactive features of the notebooks don't work in the HTML version. Or you can also start up a notebook server on Binder, which is a cloud service that allows you to run Jupyter notebooks in the cloud. And we have things set up so that if you just click this link, let me open that in a new tab. If you click that link, it starts up a virtual machine that's running these notebooks and that has all of the software installed that you need in order to run them. So that actually opened pretty quickly. Sometimes it takes a little bit longer. So I already had that open in another tab, but let me close that other tab and we'll use this one. So in this set of notebooks, we have a preface and introduction that you might be interested in, but the first one I'll look at here is the Advection notebook. You open that in a new tab. And so this is a notebook that's running live on the cloud. It's on this mybinder.org site. Some of the code, a lot of the Python code that's behind the scenes here is hidden in a Python file that you can inspect if you want to by clicking on this link, or you can look at it on GitHub by clicking on that link. I'm not going to go through that here. And there's some introduction about conservation of mass and advection, which we've already seen. So then we get to the executable cells. The first couple cells just set things up to run in the notebook and create the plots right in line as we go along, and use some of the widgets that make it easy to interact with things. And then the first interactive widget here just draws the characteristics in the xt plane for an advection equation. So these are just the straight lines. X minus at equals some constant for different values of that constant. And it's shown here for one particular value of the advection velocity, a equals 1. But we can adjust that by moving the slider bar and see how the characteristics change if we go down to a equals 0.1, or if we go negative even, then of course the characteristics move off in the other direction. And so the solution we can think of as simply being constant along these characteristic curves. And so this just shows this red curve down at the bottom is some initial hump, and then this is kind of an overlay of the solution Q in red on top of the characteristics in black, but it's meant to show that as time evolves, that whatever initial hump we give it simply advects with speed 1 in this case. Here we've used a instead of u as the advection velocity, but it's the same advection equation. If we decrease the advection velocity, then it's a little easier to see what these solutions look like at different times. And then finally, if we look at the Riemann problem, where we have this piecewise constant initial data, then we have basically the same picture, except now it's a discontinuity that's propagating with speed a. And finally, here we have what these waves look like in the xt plane, along with what the solution Q looks like at different times. So the initial data, there's a jump discontinuity at 0. As time evolves, that will move to the right. So if we move the slider bar for t at some later time t, the dashed line shows us that now we're at t equals 0.2, and a slice through the solution at that time is shown over here at the right. So it has advected to the right. Here we set a equals 1 as the advection velocity, so at time 0.2 it is advected a distance 0.2. If we go up to time 0.6, it's advected to 0.6. So you can play around with these widgets, but you can also go in here and change the advection velocity if we wanted to. For example, let's see what happens if we say -1 instead and we execute this. Then we see something similar, only now this initial data is propagating to the left. Okay, so this isn't very exciting for advection, but we'll see exactly the same sort of interactive Riemann solvers for more interesting systems as we go along, and so it might be useful to refer back to this notebook. Again, we'll look at acoustics in a minute. In fact, we'll look at acoustics right now. So remember that for the acoustics equations, the linear acoustics equations in one space dimension, our matrix A has this form, where K is the bulk modulus and rho is the density that we're linearizing about. There are two eigenvectors that correspond to left-going and right-going waves with speed -c0 and +c0, where c0 is the square root of k over rho, is the wave speed, the speed of sound in this particular acoustic simplification. And also we define z to be rho times c, or the square root of k times rho is the impedance. And that z comes up in the eigenvectors here, r1 and r2 are proportional to -z1 and +z1. And remember that if we have a pure one wave, a wave that has variation only in the r1 direction, then it simply propagates to the left with speed -c0. And if we split up arbitrary initial data as a linear combination of a left-going wave and a right-going wave, then we have these two sets of characteristic families going to the right and to the left. And this, I guess this particular splitting was from the example we were looking at where we had some variation in pressure and initially zero velocity. But more generally, you would split up whatever initial pressure and initial velocity you have into eigenvectors, and that would tell you the solution at any time. But now let's look at the case of the Riemann problem. So the Riemann problem, again, is very special initial data where we have piecewise constant data. So Q is either Q left or Q right, but Q now represents our vector Pu, so it's either pressure PL and velocity UL on the left, or PR and UR on the right. So in the special case where the U's are equal to 0 and we just have a jump in pressure, this is what's sometimes called a shock tube, or in the sort of simple linearized acoustics case, where you have two gases with a diaphragm separating them at different pressures, and then you let that diaphragm burst and you get some waves that propagate away from this. For nonlinear gas dynamics, shock tubes were used extensively at one time to sort of understand the properties of gases and what sort of shock waves propagate in gases. But here it's just our mathematical formulation of a sort of a bursting diaphragm with, say, high pressure on one side, low pressure on the other side, and, for example, zero velocity everywhere. And if that's our initial data, then what happens is that we get two acoustic waves propagating with speeds plus and minus c. And in the case of zero velocity on both sides, each one of those waves will have a jump in pressure that's half of the original pressure, and those two pressure jumps will just move off in opposite directions. So at a later time, the pressure will look like this. The velocity will also vary because the fluid will be accelerated to the right and will actually be moving to the right in between these two waves, but I'm only showing how the pressure varies here. But this would be kind of like a bursting balloon in one dimension, a popping diaphragm that sends out a little pop in each direction, and we get a jump in pressure, equal and opposite jumps in pressure moving in each direction. Here's another picture of the same thing where we're showing it sort of in the xt plane in the middle here. This is the xt plane where we started with initial states QL and QR with a jump discontinuity at the origin, and as time evolves we get two waves moving out with some intermediate state QM in between. And since it's a system of two equations, we have only two waves moving out, so there's just a single intermediate state in here. And then what we see at the bottom is sort of the initial pressure and velocity, and again I'm taking the special case where U left and U right are both zero, and that evolves into something at some later time that's shown at the top where we have a jump in pressure and a jump in velocity that are both moving out away from this initial Riemann problem, and the jump in pressure, it turns out, across each of these waves in this special case with zero initial velocity will be the same, and the jump in U will also, well, they'll be sort of negatives of each other because the velocity will be, in this case, positive in between the two waves. Because there's higher pressure on the left and the right, there'll be an acceleration of fluid from left to right in between these two acoustic waves. If I'd taken larger pressure on the right than on the left, then the velocity would be negative in between. And if I'd taken a more general Riemann problem where there was some jump in U as well as a jump in P, then we'd still have this picture in the middle that there would be just two waves moving away from this discontinuity, but the structure of the solution would look somewhat different. There'd be jumps, left-going and right-going jumps that might not look quite so symmetric. And again, I'll use these script W1 and W2 to represent the jump in Q across each of the waves. So W1 is the jump in Q across this one wave, the one going to the left here. And so it's the jump between QM and QL. And then W2 would be the jump in Q across this right-going wave. So it's QR minus QM. And it turns out for the Riemann problem, these two jumps are simply eigenvectors of the matrix A, and that allows us for any set of initial data to calculate exactly what these two waves are and solve the Riemann problem for the linear acoustics problem. And the reason is that if we look in the xt plane, if we look at any arbitrary point in the xt plane, remember for general initial data for acoustics, if we were interested in some particular point here in the xt plane, this again is the t-axis going up here, then we know that we can get the solution at that point by tracing a one characteristic back to a point here and looking at the value of w1, the first characteristic variable at that point, which would be x plus ct at time 0, and then tracing a two characteristic back to another point here where we look at the w2 characteristic variable at x minus ct at time 0. And those are the coefficients of the two eigenvectors r1 and r2 that make up the solution at time t. So in general, we can construct, for any initial data, we can construct the solution at any time by tracing back characteristics in this way. But what we see in this special case of a Riemann problem is that if I do it at this point, what happened here? Oh, hang on. If I do it at this point, I get this combination. But if I did it at some other point that's in this wedge marked QM and trace back the one characteristic and the two characteristic from that point, I would still get 2 points where the one characteristic is coming from the right state, QR, and the two characteristic is sampling the left state, QL. And so the solution at this point with an X here would have to be exactly the same as the solution at the point I circled here. In fact, anywhere in this wedge, if you trace back these two characteristics, the one wave is always going to land in the QR state, and the two wave is always going to land in the QL state. And so we can see that if we decompose QL as W1R1 plus WL2R2 and decompose QR similarly into eigenvectors with weights W1R and W2R, then the state at either of these 2 points or any point in that wedge has the same value QM, which comes from tracing the one characteristic back and picking up W1 from the right state, and then tracing the two characteristic back to where we pick up the W2 characteristic value from the left state. And so this QM is the same value everywhere in this wedge. On the other hand, if we took any point over here, for example, to the left of the wedge, if we took a point here, then tracing back the one characteristic and the two characteristic both land in the QL state. And so we simply have the solution here would be equal to QL. So everywhere to the left of this ray, Q equals QL. Everywhere to the right over here, it's QR. And everywhere in between, it's this intermediate state, QM. And we can determine QM if we know the eigen decomposition of the left and right states. Or another way we can look at it is if we take the jump in Q, QL minus QR, and decompose that into eigenvectors, which means solving a linear system. R here is our matrix of eigenvectors. For acoustics, it's minus Z1, Z1, matrix with two eigenvectors as columns. Delta Q is the jump in Q between right state and left state, and alpha is a vector of coefficients. Then we can calculate alpha 1 and alpha 2 so that we've decomposed the jump in Q, delta Q, as a linear combination alpha 1 times R1 plus alpha 2 times R2, which I'll call the waves W1 and W2. Again, those are the jumps across the left-going wave and across the right-going wave. And those alphas are exactly the same as what we get from the previous slide if we subtract our expressions for QL and QR in terms of eigenvectors. It's the jump in the characteristic variable W1, That is not right. Some of these R's should be L's, because this should be W1R minus W1L times R1, and then W2R minus W2L times R2. So once we fix that, then this QM, which we saw we could calculate as a linear combination of R1 and R2 based on W1 and W2 coming from the two sides, can be viewed as QL plus the jump across the left-going wave. So we can start with QL, add in the jump across the left-going wave, and we get QM. Or alternatively, you could start with QR, subtract off the jump across the right-going wave, and that would also give you QM. So we have two different relations for QM. So this should be W1L, and this should be W2L, I believe. Okay, so this summarizes again the Riemann solution for acoustics. We have the two eigenvectors solving the linear system, R alpha equals delta Q. In this case, you can work out what the inverse of this R matrix is very easily, or solve the linear system. And what you find is that you can write the solution, the alpha 1 and alpha 2, explicitly in terms of the jump in P and the jump in U, the right minus left state for each of those, and QM has the form shown below. So in particular, if we start with this shock tube case where the U's are both equal to 0, then a lot of terms drop out here, and we find that the middle state has a pressure that's just the average of the left and right pressure, and a velocity that depends, its sign depends on whether PR is greater than PL or less than PL, and it's related by this impedance to the pressure. Okay, so another nice way to kind of look at this solution is in what's called the phase plane. And for linear acoustics, or for a system of two equations, the phase plane is the plane where we look at the two axes as being the two components of the system. So the p-axis and the u-axis for our system, where q is equal to p and u. If we have a system of three equations, then we would have a phase space, 3 dimensions. That gets harder to draw, but for systems of two equations, you can usually draw this phase plane and see interesting relations between the different states. So what's shown here are the red and the green dashed lines correspond to taking an initial state QL and QR, just two arbitrary points, and through QL, let's look at all states that can be connected to QL by some multiple of R1. Any A times R1, as we vary A, that will trace out this line through QL that's parallel to the eigenvector R1, which is minus Z1. So this line going through QL is parallel to R1, and if we take QL plus some multiple of R1, we get some point on this line. Similarly, the second line here, the green line, is the state QR plus all multiples of R2. So R2 is plus Z1, that vector, so it has positive slope, and as you vary A, any state that you can connect to QR with a two-wave lies on this green curve. So if we're trying to solve the Riemann problem now, and we're given initial states QL and QR, then the idea in the phase plane is that this intermediate state QM that we're looking for has to simultaneously be connected to QL by a one-wave, so it has to lie on this red dashed line, but it also has to be connected to QR by a two-wave, so it also has to lie on the green dashed line. And there's only one point that lies on both of those lines, these two lines, assuming our matrix of eigenvectors is diagonalizable. These two lines are not collinear, and they intersect at exactly one point, and that is the solution of the Riemann problem. So in the phase plane, we can visualize the solution as the point where these two lines intersect. And notice that it's very important that the state below is QL and the one up above is QR, because we have to move first along the eigendirection R1. I'm assuming here that I've ordered the eigenvalues. I'll generally assume this so that lambda 1 is less than or equal to lambda 2, so that we have to go from QL to QM by a multiple of R1. In order for this to make sense in the XT plane, we need the jump from QL to QM to be moving slower than the jump from QM to QR. For acoustics, lambda 1 is negative and lambda 2 is positive, but more generally, if we had a system with two positive eigenvalues, then we might have a situation where they're both moving to the right, but still we want the jump from QL to QM to be in the eigendirection that corresponds to the smaller eigenvalue, and from QM to QR to be in the direction R2 that corresponds to the larger eigenvalue lambda 2. And so if we took exactly the same two states that I call QR and QM, these two points in phase space, but interchanged them and looked at QL as being up here and QR down here, then again we would have to go from QL along some multiple of R1 to get to QM, and then from QM along some multiple of R2 to get to QR. And so we would end up with a different location for QM if we interchange QL and QR. So if you go back and forth between those two states, it depends a lot what order the states are in, and making sure that you order the eigenvalues properly in order to get the right solution here. Here's just another example. This is the shock tube where we assume UL and UR are both equal to 0. That means QL and QR both lie on the horizontal axis with U equal to 0. And then the solution, when we solve that problem, the pressure is the average of the two pressures in the intermediate state, and there's a velocity that, well, it depends, it's either positive or negative depending on whether QR is less than or greater than QL. This is a case where the pressure is smaller in the right state than the left state, and the velocity ends up being positive in the intermediate state. But again, if we switched the location of QL and QR so that we had a larger pressure on the right than on the left, then the fluid would be accelerated from right to left, and the velocity in the intermediate state would be negative instead of positive. So again, switching those two states gives us a different set of waves and a different intermediate state. Okay, so let's just quickly go back to this notebook. So here's the index again, and now let's go to the acoustics notebook. And in this case, I'm just going to go up here to cell and run all, so I don't have to execute each cell individually. Hopefully those will all run, and we can go up to the beginning again and take a look at the first few examples. Okay, so here is what we were just looking at in the phase plane, the eigenvectors, and a decomposition of a given state, a single state, into left and right eigenvectors that are the R1 and R2 eigenvectors, rather. And with this widget, you can just adjust what the density rho or the value of k are and see how the eigenvectors shift around in the plane, or you can adjust the p or u value and see how that eigendecomposition of a single state changes. The next little interactive widget shows the characteristics and some initial data, W1 and W2. If we've decomposed things into the characteristic variables, then as time evolves, those two characteristic variables propagate to left and right independently, and if you use those to recompute the overall velocity, for example, then you get the plot that's on the right. And then we come to the Riemann problem. This just shows how to calculate a single Riemann solution. But let's go down to the interactive phase plane, where you can adjust the states. So here we see a QR and a QL, and the intermediate state QM. You can adjust the pressure or the velocity in each of the states and see how that changes the Riemann solution. You can also adjust the material parameters, rho and k, which change the angle the eigenvectors make, the angle of these, slope of these lines in the phase plane. And then here's the shock tube problem that we've already looked at, and this is a slider that shows how that solution evolves from the initial discontinuity. We had a jump discontinuity in pressure and zero velocity initially. As time evolves, you get these two discontinuities moving to the left and the right. Reflection from a wall is a sort of special case where we want the velocity to be zero right at the wall, and so imposing those boundary conditions corresponds to looking at a Riemann problem where we impose that UR is equal to minus UL, and then it turns out the solution of the Riemann problem gives us the correct reflection at a wall. So we'll talk more about this when we look at boundary conditions for numerical methods, but this is sort of a prelude to that. Oh, and then there's also at the bottom here an interactive phase plane that's a little easier to play around with than the other widgets, where you can actually just grab QL or QR with your mouse and move it around and see how the solution to the Riemann problem changes as you adjust QL and QR. This is a nice little widget in JavaScript that Mauricio wrote to make this easy. So this isn't done with the Python tools that are used for other things in this notebook. And then finally, there's an example of taking some more general initial data, Gaussian initial condition in this case, and plotting the pressure and velocity, and then looking at how it evolves with time as an animation. I'm going to select just once so it only plays through once, and I'm going to press this minus sign a few times to slow it down because it goes too fast otherwise. And then if we play it, you see the initial pressure hump splitting into two pulses and reflecting off of the boundaries that were solid wall boundary conditions in this case. So that's a quick demo of what's in the Acoustics notebook. And so finally, just a summary. If we have a more general linear system, a larger system with M equations, system of M equations, and A is a diagonalizable matrix, M by M matrix, but we assume that we can write A as R times lambda times R inverse, and that the eigenvalues are properly ordered, lambda 1 less than or equal to lambda 2, and so on. Then the idea is that we can take the jump in Q and decompose it as a linear combination of the eigenvectors, and then once we've solved that, the Riemann solution consists of M waves, which we'll call WP. Each of these is basically just a vector with M components that represents the jump in Q across that wave. And the jump in Q across the pth wave is just the scalar alpha p that comes out of this solving this linear system. The pth component of that multiplied by the eigenvector Rp, and that's the wave that's propagating with speed lambda p. And as I mentioned, for a system of two equations, you can draw the nice picture of the phase plane. For a system of M equations, the phase space is M-dimensional if we look at the space of point vectors Q with M components. And so it's harder to draw typically, but it's the same idea of solving the Riemann problem consists of finding a path in phase space that goes from state QL to QR that has in general M segments, And each of those segments has to be in the direction of an eigenvector. And assuming that we've ordered the eigenvalues properly, then the first segment has to go from QL to QL plus some multiple of R1. The next segment has to go from there to QL plus alpha 1 R1 plus alpha 2 R2 for some alpha 2, has to move in the direction of the second eigenvector, and so on. And assuming the system is, the set of eigenvectors are linearly independent, we can always find alphas so that we can complete this path and end up eventually at QR. And we can find that path by solving a linear system. And again, to visualize it, it becomes hard when m is greater than 2, but sometimes it's illuminating to take a phase space and project it onto two-dimensional planes. So in particular, when we look at the full Euler equations for mass, momentum, and energy, even though that's a three-dimensional phase plane, it'll sometimes be useful to look at projections of that onto two-dimensional planes.